I'm going to begin recording and introduce our speaker this evening, Sally Jensen, who is a NASA Solar Ambassador and a retired teacher who is still teaching. And we're very glad that she's here this evening to share some really interesting information about the James Webb and Hubble telescopes. So I will let you say anything more that you would like to about yourself. And
Okay, what I'll do is explain the Solar System Ambassador Program. It's put out by NASA. It's an outreach education program, and I applied in the 90s. I've been doing this for a long time, and then they train you, and your purpose is to give presentations and talks for those who are interested. You have to apply every year, and then it's a volunteer. So we have about 500 throughout the United States and territories. And it's fun. It really connects you with people. The training is great. And I'm a space enthusiast anyway. It's, to me, things like this where countries put the finest minds together and come up with some amazing stuff for us to learn and to implement and explore. So anyway, Hubble has an incredible story, and and I want to talk about those contributions and then how James Webb will follow in Hubble's footsteps. So my goal is to go a little bit through the history of telescopes and particularly the Hubble Space Telescope, some of Hubble's accomplishments, and of course some of their images, and then how Hubble changed scientists' view of examining the universe. It was really mind-blowing. There's a video that I have coming up that will, is really touching. And then certainly our new James Webb telescope, how it will extend the story and its condition, and it's doing well. So all right. So first of all, we observe our universe by using our primary source of light, which is from the sun. And so light is all around us, and it's electromagnetic phenomena called the electromagnetic spectrum. And so we have a diagram here. And so if you look at, I don't know if you can see my arrow. Can you? Anyway, there's a little spot here, the visible spectrum, where we see, that's where our eyes are. And you realize that is a millionth, 1/1,000,000th of 1% of the measured of the electromagnetic spectrum. So that's very tiny. So our view of the universe is minuscule between all these other wavelengths. And so telescopes gather all this information at different wavelengths so we can get all this rich information. So it's pretty amazing. I thought 1/1,000,000th of 1% is, and of the measured spectrogram, because that means there's some part of the electromagnetic spectrum that hasn't been measured yet. So just like the unobservable universe. There's another diagram here, and this just shows you that different telescopes or observatories in our atmosphere, here's the Hubble in the middle, and their view of the Milky Way. Now we'll have Spitzer here, it's a different name right now, and then the Compton, which is decomped, is just simply non-existent. It's in the ocean right now, but it gave images in the gamma ray, and the University of New Hampshire was very much a part of that. And I know that this is about Hubble and about James Webb, but I have to give a shout out to Chandra, because I'm also a Chandra resource agent, and Chandra has a good story too, but it never gets any media. It's an X-ray telescope that is about a third its way to the moon, a very elliptical orbit. And so it has also contributed to the information that Hubble from that data. So they all get together, Spitzer, Hubble, Chandra, whatever's out there taking images. And so they do it together and give credit. So they're sharing information, which is nice to hear. Okay, so what was the origins of placing a telescope in space? The very beginnings came from Lyman Spitzer, and he wrote a paper saying what would be the advantage of putting an extraterrestrial observatory, a space telescope, above the atmosphere in Earth, because air and clouds and everything kind of muddy things up. And then I said, okay, so Spitzer had that idea. Where did he get it from? And he got it from one of the three fathers of modern rocketry, Hermann Oberth, who in 1923 wrote a book, The Rocket into Planetary Space, and one of the chapters happened to be on having a rocket with the ability to go launch a telescope into space. Okay, and so then historically, the dawn of the space stage, and this is important, happened to be in 1957, October 4th, the Soviets launched Sputnik. Now, I remember that as a little girl, and I remember hearing it and was scared to death. But anyway, it was about the size of a basketball. It weighed about 183 pounds, and it took 98 minutes to orbit the Earth in a very elliptical path. And I do have, I don't know if I should, the sound of it. Oh no, I guess it didn't. Well, we'll skip that part. It didn't do the sound. So anyway, and the importance of that is ever since that satellite, that artificial satellite was successful, it changed how we explore Earth. It changed everything about how we explore space and what we do. And that's key. One of the key things, we used to just walk the Earth and map it out, but now we do it very differently. So before Hubble, in 1966, an ad hoc committee was formed to study and research the possibilities of an Earth orbiting telescope. Okay. And then in 1969, the committee published the scientific uses of a large space telescope. And the National Academy of Science advocated for the construction of such an instrument. Now, how to do it? So, okay. And also, I have to put in here during the 60s, there was a lot going on politically and a lot going on exploring, because we were doing, NASA was doing space missions to the Gemini, the Mercury, the Apollo, you name it. So that was really a lot going on. And I always thought the Hubble was the first large telescope that orbited Earth. I mean, it's the large one, but there were four observatories launched in the 60s called the Orbiting Astronomical Observatories. And a couple of them were there quite a few years, and one of them was there almost 10 years, called Copernicus. So that was a misunderstanding I've had, a misconception that Hubble was not the first large one, maybe. Okay. How did Hubble become a reality? Okay, so here we have the 60s. NASA started studying this idea. Okay, and then in order to get a large space telescope up, you have to get something to take it up, a big rocket or whatever. So there was the development of the space shuttle. And then in 1970, NASA took up the idea and proposed a 3-meter space telescope, and they went to Congress. And it was rejected. It was turned down. It didn't even get to the floor. It got turned down by the subcommittee. So now what? What do you do when you get rejected? You go back to the drawing board. And what they did was they included the European Space Agency to help with funding, and it created a very international effort. The mirror went from 3 meters to 2.4 meters, lowering the costs to 400 million to 200 million. And the proposal was accepted by Congress, which granted the Large Space Telescope program, and that funded, and the acceptance was 1977. Okay, but it took a while before we get to the point of launch, fuzzy photos, and a spectacular repair. So the original date for the Hubble launch was 1983, but that was delayed. But there were 2 exciting things that happened also in the meantime. The founding of the Space Telescope Science Institute at the Johns Hopkins University in Maryland would be one to do the research for Hubble, or when any telescope goes up. In other words, what happened is when an observatory goes up, scientists apply saying, I want time on that telescope to use it for this research, and then they're accepted. And so there's constant reviews and constant research data that's continuing to this day. And there's just an immense amount of data still being researched. And then the naming of the telescope, which after Edwin Hubble, who did extensive research on stars and galaxies. The next date for Hubble's launch was October 1986. But the tragedy in January of the Challenger disaster really delayed that. Hubble was finally launched on the Discovery in 1990, but the first images that came back were very fuzzy. And so what happened is the engineers were able to figure out in a relatively short time, because they went up in 1993 to service it. And there was a mirror aberration that just didn't work. And there was a miscalibration of measurements. Okay. So this gives you a kind of a timeline of some of the service missions. Hubble was designed to be made better. It was designed that you can go up there because it was in an orbit that you could reach it. It's the only telescope that had that capability. We won't be able to do that with the James Webb. We haven't been able to do that with the Chandra, even the Spitzer. So anyway, so by 1993, they repaired the primary mirror, and then they added new instruments, and then in 1999, there was a gyro replacement, and these gyros kept the telescope balanced. And in March of 2002, solar panels were refurbished. There was an advanced camera, and so then in the last mission, 2009, it was really again almost like a new telescope, because they went up and did a lot of refurbishing. And this is just some images of some of the spacewalks, which is I just find interesting that they were able to do that. And there's videos, and it's just amazing all the things that they have been able to do, which they're doing now on the International Space Station. Okay, so here's Hubble's images. The first image came back really fuzzy. Okay, and after the first repair, we can see the difference. And this is of a galaxy. I forgot the name of it's a galaxy that's was in the Big Dipper constellation, and it's about 6 million miles away. 3 facts about Hubble. It travels at the speed of 17,500 miles per hour and has covered the distance which is equivalent so far to a trip to Neptune. Hubble can peer back into very past distance to locations more than 3.4 billion light years from Earth. And since its mission began in 1990, Hubble has been made more than 1.4 million observations. And some more things that they've contributed to science is it's helped pin down the age of the universe, now known to be about 3.8 billion years, roughly 3 times the age of the Earth. It discovered the 2 moons of Pluto, Nix, and Hydra. It helped me determine the rate at which the universe is expanding. It discovered nearly every major galaxy has a black hole in the center. And then it created a 3D map of dark matter. It also has been able to analyze the atmospheres of planets around other stars. It monitors the weather changes, and so we're going to be going, hopefully, to the planets of our solar system. And so it's giving us the data we need because we need to know the weather and be able to predict it. There has been over 7,000 peer-reviewed scientific publications. And the archival data alone will fuel future research, even after, let's say, when Hubble, is on this. There's no more service missions for Hubble, and so there's plenty of data for people to research and do their doctorate and finding interesting things about our solar system. Edwin Hubble, he was the one who. The scientist that at Mount Wilson in 1924, using a Hooker telescope, 100 inches, he began to study other galaxies other than the Milky Way, and he was finding out that they're almost moving away from each other. And so that was the first suggestion that the universe was expanding. Well, he started this idea, and that let out a whole Pandora box of scientist inquiry and beginning to the possibility of what's happening to our universe is expanding. And so that's why, appropriately, the Hubble telescope was named after him. Okay, now, one of the observations that somebody decided to do is they took a black patch of sky and they focused on that small patch for 11 consecutive days. And I have a video, and it has music and there's reading on it. I won't do any talking because it's very impressive, especially when this patch at the end, it's very moving. It's humbling, to be very honest with you, as to what this patch did to scientific research. So that was only one patch. And you think about it, it's just amazing to me. And those are, we haven't even gotten out of our own, on our own solar system, which is in the boonies of the Orion arm in our own Milky Way. So that's just amazing. I think it's just humbling to see what vastness there is to explore. It's just, and the evolution of how galaxies form. And this is an image of Hubble, and it's nicknamed Cosmic Reef. And it was taken on Hubble's 30th birthday. It's been up there for 30 years as of 2020. And so this is a galaxy near the Large Magellanic Cloud. And its center is much more massive, about 10 to 20 times more massive than our sun. And this is a video which I'm not going to show you now. If we have time, I will. So it just gives more images that we have seen. There we go. Nancy Grace Roman is a key figure that I wanted to bring in because she contributed to the development, and people highly think of her highly. She contributed to her work on developing an instrument, a telescopic instrument with a refracting capability. And so she's been part of all the different missions, but especially the Hubble mission, and people have regarded her contributions. And she died in 2018. The James Webb Telescope. Okay, it's another infrared telescope, approximately 6.5 meters in the primary mirror, and it was launched in 2021, just a couple months ago. The mission is to seek light from the first galaxies of the universe and to explore distant worlds. It's to be used by thousands of astronomers worldwide. And again, it's led by not only NASA, but in partnership with the European Space Agency and the Canadian Agency. Now, who's James Webb? He was the second director, administrator of NASA. And he always was strong in pulling in a science program for NASA, but he was involved with all the Apollo program, the space shuttle, the Mariner program, Pioneer program. There's so much that NASA is doing because different missions that they're working on, and we focus on from the news point of view, but then there's other missions they're focusing that affects every other mission, like the shuttle program. If that wasn't developed, we wouldn't have been able to get Hubble up. And so anyway, so it was named after him. And if you notice, I have recognition given to different people on some of my slides. I use some of this information, and that's during the training when you're a solar system ambassador, or if you're part of any other mission, then you get the training. And so we're allowed to use some of the information they have given us. So let's compare the two telescopes. So here's Hubble. If you look at the mirror, it's 2.4 meters, and James Webb's is 21.3 feet or 6.5 meters. The length, Hubble's a lot shorter, 44 feet, and a lot heavier. Look at the weight. It is almost half the weight, and it has to be because it's huge. So they have to, and the less, if your instruments that you're taking up to explore, way less, it's easier to get it up there successfully. And man, we were all waiting in bated breath to figure out if this was really going to work, because it's the most complicated telescope ever created. So the wavelengths, Hubble is mainly visible in near infrared, whereas the wavelengths is going to be visible near infrared and the mid infrared. And the temperature of for the Hubble is at 7 degrees Fahrenheit. Okay, temperature for the James Webb, it has to be very, very cold, 370 Fahrenheit. This is a schematic, again, showing you, as we look into the past, the limitations that Hubble had. And on the right side, if you notice, that's part of the electromagnetic spectrum. And it's going from the visible up in the upper part to the infrared. And so it's giving you an illustration about how far Webb's limit is going to be to add to what Hubble has already started on their story. What powers the James Webb Telescope? Okay, so there's an electrical power subsystem that provides electricity to the spacecraft, and that consists of, you got solar panels, and you got rechargeable batteries, a solar array regulator, a control unit, telepathy acquisition unit, and the solar panels convert sunlight directly into electricity. Now, I show a lot of the electromagnetic spectrum because that's the very basis of how we study our universe. So it shows you the Hubble Space Telescope is mainly in the visible. It does overlap a little bit into the near infrared. And here is the James Webb Telescope. And look over here, another scope, the Spitzer telescope, which is now, I think it was a year ago that it stopped functioning, but it also has an incredible story like Chandra and has contributed a lot to add to Hubble's findings. So it looks like the James Webb is not going to go as far into the electromagnetic spectrum as the Spitzer. But that gives you an idea of where the span is. Location. Hubble is orbiting about 350 miles above the Earth, and the James Webb is orbiting the sun around 940,000 miles at a point in the orbit called Lagrange II. And what that is there's different points along the orbit that has a relative, like a balancing point. And different space missions in the past have used these points along the, orbiting around the sun, because it saves fuel. So it's a balancing thing. So the pull and the tug on gravity is pretty balanced. And so it's at L2, and it's there. Okay, two main innovations. Here we have the mirror, okay, and so it's made of beryllium. It's 6 stronger times that of steel, and it's 2/3 less dense than aluminum. And it's coated with a very thin layer of gold, which is the most reflective material for infrared. And it is so thin, it's about 1,000 atoms thick. I don't know how they did it, but anyway, that'd be interesting to see. All right. And then Sunshield. Now, the Sunshield consists of 5 layers of polymer material called Captain, and each layer is coated with a vapor deposit aluminum. And then the 2 closest layers to the sun are also coated with a silicon, because it's going to get the most intense heat and it will protect it from the sun's ultraviolet radiation. Now, this Sunshield, as it was deployed successfully, is the size of a tennis court or a 10-car parking lot. And if you think of plastic wrap, that's how thick these are when they're spread out, and they can't touch each other. You can't touch each other. Okay, and this is kind of a diagram showing you that the part that's facing the sun, so the sunlight comes in and you can see the sun shield protecting it. And then you got the cold side. Now look at the difference at the temperature. between the hot side, 185 Fahrenheit, minus 388. That's really cold. But it's got to be that way. The reason it's cold, because that makes it so that is less interference at that wavelength for the infrared. So there's no other interference when you're looking at an object. So how do you get a huge telescope like James Webb into a rocket ahead? So you got to fold it up. So that's what I love about this, because it's cross-curricular. They use origami. And James Webb is not the first space mission in order to use origami, which is a Japanese form of art and paper. And so here's another video that just shows you how, if we observe and take things we do, how they all can connect.
Origami is the ancient art of Japanese paper folding. For years, it has been used to create stunning works of art. But origami has also been used in more surprising ways, like car airbags, stents, and even space exploration.
What we want in space are large structures, not necessarily massive, but large, which means you can make them out of thin materials. And wherever you can make them out of thin materials, you can use origami to fit them in these rockets.
Many space projects have used the folding principles of origami. The solar array wings on the ISS use the Z folding pattern, and the Mars Phoenix lander used a fan folding solar array called the Ultraflex.
Because the biggest rockets we have right now are only about 5 meters in diameter, we have to come up with a way of folding up this very large structure into space so that we can launch it inside a rocket. And once it gets to space, it can unfold itself. And origami is one mechanism by which we can do that, because it gives us the underlying mathematics of how large, thin sheets fold up.
One origami project currently in development at NASA's Jet Propulsion Lab is the Star Shade, which is essentially a big star blocker. Have you ever tried to take a picture of someone when the bright sun is beating down on them? All the detail gets washed out. This is the same problem astronomers have when trying to image exoplanets. Currently, astronomers detect exoplanets indirectly using a shadow technique called the transit method. For an Earth-sized exoplanet orbiting a sun-like star, they can't be imaged in detail because the stars they circle are much brighter than they are. This is where the star shade comes in, to help block that bright light to better help astronomers learn more about these mysterious planets and look for biosignatures for life.
One of the ways in which we're thinking about suppressing the starlight is using something called star shade, which is a very large external occulter that flies in front of a space telescope and blocks out that starlight so you can image a really faint planet right next to it.
Sounds easy enough, but the star shade is roughly the size of a baseball diamond.
Because the star shade is so huge, we have to come up with a way of folding up this very large structure into space so that we can launch it inside a rocket. Once it gets to space, it can unfold itself.
Which is where origami comes in.
So this is one of the candidate fold patterns that we had for the inner part of the star shape, what we call the optical shield. It's got a very deterministic shape when it's folded up, so we designed it to have this shape in which it can account for the thickness of that blanket. You can mathematically define how this sheet of paper is folded up. The way it unfolds is like that, and it creates these very nice spirals inside the folded structure. It's quite remarkable in its simplicity.
This giant space flower may seem simple in design, but not in implementation. The star shade will need to unfold with millimeter accuracy. Once opened, thrusters will move the craft through space, positioning the star shade between the star and the space telescope. With the star now being shaded, the telescope can image the planet in detail to find out whether conditions for life exist. Origami has been practiced on Earth for years, and scientists will continue to draw inspiration from it to help package big space structures more efficiently, from solar sails that use sunlight for propulsion to sunshades for telescopes like Gaia and the James Webb once it launches in 2019.
We can take these ideas from origami and apply them to spacecraft structures that way.
Because when it comes to the future of space exploration, if we want to think big, we also have to think small. For more science documentaries, check out this one right here.
There we go.
Don't forget to subscribe and keep coming.
There. So, and also the sections of the mirror, there are 18 of them, I believe, are hexagons, so there are no gaps. They couldn't make it circular. So, but I thought that's just really cool that you can do something that you love in making something, and yet it can apply to how we explore. The Perseverance mission, which is on Mars, the little helicopter. Scientists got that idea for the helicopter from watching insects, because it looks like a little insect, and they were able to observe and make that connection. So it's really working remarkably. So the James Webb scope was launched in a little country called Kourou, French Guiana, and it's in South America. And it was launched on Christmas Eve. And it was just breathtaking to see, will this succeed? Because this is the most technical feat in order to get it going. And it's been so successful so far. This is a very famous image of Hubble, the Eagle Nebula, or they call the Pillars of Creation. And this is taken in different wavelengths. The one on the left is in the infrared, and the one on the right is in the visible. So there's a remarkable difference between the two that you see. And this is we're getting close to the end of the presentation. It just gives you a summary of this development of the James Webb Telescope. And again, these videos were taken before it was launched, so they're still applicable, but the information it's already launched. So.
This is your telescope, an engineering marvel, an exploration powerhouse. Use it to look back in time and explore the first galaxies that formed after the Big Bang. To peer into atmospheres of planets orbiting the stars. It's your eyepiece to the uncharted, unknown, and unimagined. This is the largest, most complex, and challenging space telescope ever constructed. It will change our understanding of the universe and our place in it. The James Webb Space Telescope. Equipped with the largest primary mirror ever to be flown in space, at 6.5 meters, it's more than 6 times the size of the Hubble Space Telescope primary mirror. Webb's 4 cutting-edge infrared instruments and cameras operate at super cold temperatures colder than the surface of Pluto. Getting this cold is done with the help of the largest sunshield ever flown, a 5-layer, tennis court-sized sunshield that blocks heat from the sun, earth, and moon. Webb will be the first telescope to detect light from the most distant galaxies in the universe. These first galaxies formed about 13.5 billion years ago, only 300 or so million years after the Big Bang. Webb carries advanced technologies to tackle some of the most fundamental questions about the universe. How did the first galaxies form and evolve? Are there chemical signatures of the building blocks of life on other worlds? Is our solar system unique? Launching such a large telescope into space is an incredible engineering challenge. Fully deployed, Webb is too large to fit inside any rocket fairing. Engineers designed it to be folded, like origami, to squeeze inside the European Space Agency's 5-meter diameter Ariane 5 rocket fairing. After launch, controllers on the ground deployed Webb remotely. Deployment is an intricate ballet. For nearly 3 weeks, controllers carefully unfold Webb. After this delicate dance, Webb's golden mirrors are precisely aligned using motors behind each hexagonal mirror segment, adjusting them to form one perfect mirror. Once the instruments are fully cooled, the exploration will begin. Webb is a technological challenge like no other, born of the efforts of thousands of people across the United States, Canada, and Europe. The James Webb Space Telescope is your telescope. Use it to explore, to challenge theories, to see sights yet unseen. It's yours to unfold the beauty and mystery in the universe and our place in it.
Okay, so now it's cooling down. It's deployed the mirror, everything so far successfully. And as of they said February 3rd, they're beginning to capture and calibrate the photons the mirrors are collecting, so that it will be probably in June when they get their first image, because they're still cooling down. And so it just takes a long process. And so what will the James Webb be able to observe in our solar system? What it will not? It will not be able to observe the sun, Mercury, Venus, the Earth, and Moon, but all of the outer planets, including Mars, it will be able to. And I thought that was interesting to figure out. And these, I had a lot of people help me with this. It was Dave McDonald, who is a teacher, and he wanted me to do a presentation, and so I gave him a couple ideas, and he wanted me to focus on this one. And so, and then I have some neat colleagues who are always giving me some help and encouragement. And then we have scientists who have contributed to this presentation. And that's it.
Excellent. Thank you very much, Sally. That's great. It's so interesting to.
Oh, isn't it? It's just so amazing. And I'm just like, this is what I love about space, because the spin-offs of NASA and these technologies spin off into our lives. And so there's another whole presentation about, so NASA just isn't in space, it's everywhere. It's in our computers, it's in our medical advancements, it's in the research, it's doing all this data collecting, and it's just so amazing. So it's just, to me, beautiful.
Excellent. Well, I appreciate you coming on this evening and sharing the information. And we do have a couple minutes if anybody wants to unmute and check in. Otherwise, again, this presentation will be on our website, recorded for viewing later. And I know that looks like Mike just unmuted himself, but I'm not sure if that was just to say anything or if it was just to check in.
Just checking. You don't have a question. We just wanted to say thank you.
Thank you for coming this evening.
Yeah.
And I'll have links underneath this presentation to a few of the topics that Sally covered. And maybe we can have her come back and do a little bit more, definitely, as we get ready for the eclipse in a couple more years. It's going to go by quick, for sure.
We got to be ready because we're going to get a lot of it. It's going to be even better for New Hampshire than the 2017 eclipse.
Yeah.
Yay.
Yeah, we have to be ready. And I have glasses for it.
Oh, good.
Get your glasses. So.
Oh, it was pretty great how many of those we went through a few years ago.
Yeah, well, we have to get them early.
Yeah.
So.
Oh, and
Mom.
Go ahead.
Well, unfortunately, I know too little about this science, but this was so phenomenal. I mean, doesn't it change your whole worldview? I mean, to go out into what we've just thought of as three-dimensional, as two-dimensional, looking at from the night sky, if we're lucky enough to see stars, and then think about the dimensions of that. I know.
Yeah.
It's pretty amazing.
And we're only in one tiny we're only a little speck in that patch, and there's so many patches. I mean, that one video to me was very, like I said, humbling. Because
well, I mean, if people realize, if more of us realized this view, I wonder if we would be a different species.
right.
Well, maybe we'll live long enough to be that way. To be a different species. Mike, you have your hand up. No. Yes.
Do you have a question, Michael?
No,
Then
I
put
don't.
your hand down.
I have my hand down.
I'll lower it on the screen. All right. Well, thank you all again so much. And Sally, thanks for joining us. Our next presentation for March will be Jack Sanders, and he's going to talk a little bit about the beginnings of freestyle skiing. So we're going to go back and forth between science and skiing. But I bet if we looked into skiing right now, I bet some of that technology comes from NASA in some way, shape, or form.
There's a lot of science in that skiing. So
yeah, no kidding. Excellent. Well, thank you so much again, and have a nice evening, everyone.
Thank you.
Okay.
Thank you. Night, night.